Now we're going to use Gauss's law in order to calculate the electric field everywhere around a long, hollow charged cylinder. You can imagine just how ridiculous this problem would be if you had to use Coulomb's law. So here's our cylinder. From the end, you can see that it's been hollowed out, and let's give it an inner radius of A and an outer radius of B. And we'll look at it from the side as well, just so you can get some perspective. So imagine a material like Perspex, and it's going to have charge all the way along it, inside the material, on the surface of the material, and so forth. Now the question is, what is the electric field that this generates? Okay, so if we want to find the electric field somewhere around this rod, we're going to use Gauss's law. And we need to use some very tricky symmetry as well, and we'll find the electric field in quite a simple way. The first thing is to think of a good shape and position of a so-called Gaussian surface. I'm going to use a cylinder because it matches the symmetry of the rod, and I'm going to place it so that the center of that Gaussian cylinder lies along the center of the long rod. Let's extend our rod along here. And now I shall put my Gaussian surface around it. Okay, now I'm going to make this Gaussian surface have a radius that's larger than B, because I want to find out, in this case, the electric field outside of the pink long rod. You could make it smaller if you wanted to find out the electric field inside. The dimensions we'll give it is a radius r. Of course, this is not the displacement vector, just a radius r and a length L. Okay, now we have to give it a length because our Gaussian surface needs to be finite. The charged rod itself is practically infinite in this case. Okay, so we need to find the electric flux through the surface of this Gaussian surface, and then we need to find the charge enclosed. It's easiest to start with considering the charge enclosed. If we look at it from end on, here's our Gaussian surface like this. Then the charge enclosed is going to be the charge density in here, the whole rod, multiplied by the length, and the difference in the areas of these two circles. That's to get the volume, isn't it? So I'll use green. The volume of the outer cylinder is going to be pi radius squared, which is b, times the length L. The volume of the inner cylinder is going to be pi times the radius squared times L as well. So our difference in area is going to be pi L b squared minus a squared. And that's going to give us a total enclosed charge of the charge density, rho coulombs per cubic meter, times the volume, pi L b squared minus a squared. Okay, now let's move on to something that's a little trickier. We need to find the electric flux through the surface. It takes a little more thought. Now, we expect that the electric field outside the rod will always point outwards. As opposed to doing something like this. Okay? So it's always going to point outwards, and it's always going to be at right angles to our Gaussian surface. So there's a little right angle there. Of course, that right angle means that our area element, dA, is going to be parallel with the electric field there, isn't it? Now you see why I chose this tricky geometry. Let's calculate the flux. Remember, the flux through the curved surface is going to be the electric field by the area. And the dot product says that if our vectors are parallel, then we simply have to take the scalar product. Easy as that. In which case, our integral simply becomes the electric field times the area of the curved surface. Now, the area of a curved surface of a cylinder is 2 pi r times the length. So now we have the flux through the curved surface. Now, of course, we also have to work out the flux not only through the curved surface here, but also through this flat surface, because we need to have a closed shape. So we'll next see how we can do that. Now, if we want to see what the electric field is doing through the flat end surfaces of the Gaussian cylinder, we'll sketch it. We'll sketch the rod in a side view like this. There's the inner hollowed out core there. Now we expect that the electric field is actually going to be going in this direction, don't we? If we put on the Gaussian surface, you can see that that is parallel to the end surface. Okay? What we don't expect to see is an electric field that is sort of tilting one way like this or tilting another way. So that's not going to happen. We expect it to be parallel to the end surfaces of the cylinder. And this here is, of course, our direction dA. That's the area element on the end cap. And this is our electric field. Now you can see that the electric field direction is perpendicular to the area element direction. It means that as you can see, there's no electric field flowing through this end surface. Formally, the dot product of the electric field vector and the area element vector is 0. So the flux through the end caps is 0. So we don't need to take that into account. Now we're going to use Gauss's law. We've got the flux, which is basically the flux through the curved surface, and we have the charge enclosed. So Gauss's law says we've got the flux through this curved surface, which is 2 pi times the electric field times the radius of the Gaussian surface times the length of the Gaussian surface, is equal to the charge enclosed. And the charge enclosed is given by the charge density times the volume times the constant of proportionality. So that's what Gauss's law tells us. Let's neaten this up a bit. We can cancel pi from both sides. We can cancel L from both sides. And we can rearrange it to give us an expression for the electric field. This gives us the electric field is given by 1 over 2 epsilon naught times its charge density times the difference in the squares of the radii divided by r. So r is, of course, the radius of the Gaussian surface. So that's going to give us the electric field at this distance here, r, from the centre. If we made our Gaussian surface bigger, that would be a larger r, and we can work out what our electric field is then at the larger r. So this expression gives us the electric field everywhere outside this cylinder. So the full version, the vector version of the electric field, of course has a direction, doesn't it? It's always going to be, we said, pointing outwards in the direction of r. So this becomes the electric field, the vector, and we put the unit vector r there. R is in cylindrical coordinates. It starts at the center, the axis that runs along the center of this rod. So isn't that wonderful? We've done actually some very simple maths. It wasn't onerous at all, and we can now describe the electric field, the strength of it, and the direction of it everywhere around this unusual charged object. So Gauss's law can be really useful to get an exact expression in order to describe the electric vector field for these symmetrical systems. We just need some intelligent guessing of the electric field directions. Coulomb's law is going to give us the exact electric field at one point due to a stationary distant charge. But Gauss's law makes Coulomb's law a lot more usable.